Let's talk drag force equation. We're going to be using this equation quite a bit this semester, mostly with swimming and cycling, a little bit with running, but primarily swimming and cycling. The reason is swimming is being done in the water, and the water is very dense, and cycling, you're moving very fast. And so drag force can really play a role in both of these sports. Running, it can be it can be a factor if the wind is strong. Maybe you're also trying to go under 2 hours and you draft behind people or a vehicle to try to make as little resistance to moving forward. All right, so let's go through the equation and make sure we understand the parameters in each equation. All right, so the equation is F drag equals 1/2 rho RHO CD A V squared. So 1/2 rho CdA V squared. Each of these parameters are defined here. The unit for drag force are units of newtons. It's a force, and it has a just has a special name called drag force. Rho, RHO, is fluid density. It's how thick the fluid is. It's the unit for density are mass per unit volume. Air has a density of about 1.2754 kilogram meters per meter cubed. This can be dependent on altitude, humidity, what's in the air. Water has a density of 997 kilogram meters per meter cubed. And again, this is influenced by what's in the water, salt water versus fresh water. V, which is at the end of the equation there, V is velocity of the fluid moving over the object or relative to the object. It's not the velocity of the object. Okay, so big distinction. It's velocity of the fluid moving relative to the object, or how fast the fluid is moving over the object. So cycling into a headwind, we want to know the velocity of the air moving over the cyclist, not how fast the cyclist is going. Swimming in the water, we want to know how fast the fluid is moving over the swimmer, not how fast the swimmer is going. Obviously, we're interested in how fast the person is going in each of those examples, but to calculate drag force, we just need to know the velocity of the fluid moving over the object. The units for velocity are still meters per second. CD is coefficient of drag. This parameter is based upon the surface characteristics and shape of the object. It's a classic teardrop shape, okay? It represents how easy it is for the fluid to move over the object. It's a unitless parameter. So you may hear a cyclist talk about having actually, let me jump ahead because they don't talk about CD by itself. So I'm ahead of myself there. But it could also be determined by how smooth the object is, or how easy it is for the fluid to move over the surface of the object. Okay, so it's partly based on shape and based on surface characteristics. So if I'm trying to reduce CD, I would have a smooth, or I'd have a surface that the fluid really doesn't stick to. So if you want to think smooth, that's fine. There's actually some better surface characteristics. It doesn't always have to be smooth, but we just want to make that fluid move over the surface really easily. A, the last parameter here, is frontal area, and the units are meters squared. Now, frontal area is just the perpendicular area relative to the fluid. So whichever way the fluid's moving, we figure that out. And then we look at the object and we look at the frontal area, really the cross-sectional area of the fluid hitting the object. So if we're thinking about a cyclist, it would be, and I'll show a picture in a second here, it'd be the front part of the cyclist. Or if we think about a big 18-wheeler truck, if you look straight on that truck, that shape that you're seeing, the outline of the truck would be the frontal area. And that's obviously larger than the frontal area of a car. And therefore, that partly explains why a truck would have a greater drag force when driving. Now, it's very common, and we'll do this, and I almost did it just a minute ago, it's common to combine C, D, and A into one parameter, so as a single term. Why? Because sometimes changing one changes the other. And sometimes in human movements, it's hard to separate out these two parameters from each other. So where I was going before is you may hear a cyclist talk about their CDA, what their coefficient of drag and frontal area are, what that is for a particular position. So I heard on a podcast the other day, a cyclist was talking about getting his CDA down to 0.19. Usually when you're riding with your hands on the handlebars and you're upright, your CDA could be maybe 0.3 or 0.35 even. So getting the CDA collectively down as low as possible is a good thing because it's going to reduce the drag force. Okay, so what we will, and you will see in the reading, if you come across drag force literature, it's not unheard of to combine CDA and talk about that as a single term, but it's actually two terms. All right, so drag force, we typically think as a resistance force, and that's true. It can be a resistance force in running and cycling into a headwind, swimming against the water. Those are examples of resistance forces. So clearly, if a cyclist is biking into a headwind and this wind is hitting the front part of the cyclist, you have to overcome that. And if there was a current here, if you're swimming upstream, which is not uncommon in endurance swims, you can have courses where you're swimming against a current. Louisville, for example, Chattanooga. Well, Chattanooga is mostly downstream, but there is a section of upstream. So resistance forces, where the fluid is pushing against the swimmer or cyclist in a way that is opposing motion. But drag force can also be a propulsive force, a tailwind when cycling or when running. So the wind's pushing from behind. And here in Las Vegas, we get some pretty strong winds, especially in the spring. And it's not uncommon to have wind speeds of maybe 30, 35 miles per hour at times. And if that catches you from behind, that's going to be pushing you. So that drag force ends up being a propulsive force at that point. Swimming, the same thing. Swimming, it can also have a propulsive force due to drag. Where is that? Well, it's actually at the hand. What moves a swimmer forward is the drag force pushing on the hand, which is pushing in the direction of motion, because the swimmer's trying to move the hand backwards through the water, but drag force prevents that. And that prevention of the water pushing on the hand is what actually propels the swimmer forward. Okay, so we'll talk about that in the swimming kinetics lecture. So drag forces can be resistance forces or propulsive forces. So here's our equation, 1/2 rho CDA V squared. How do you reduce drag resistance force during cycling? Well, reduce density of air. Well, you can't do much about that unless you're trying to, it's very, cyclists who are trying to break the hour record, for example, they may actually go pick a course based upon the density of air. They may pick a time of day to do their event based upon the density of the air, when humidity may be such that density is lower, or you pick a course at altitude that density of air is lower versus at elevation. Okay, so that's, you could do that. Most of the time, you have no way to choose or to influence density of air, but you could choose tight-fitting clothing. You could change your aero position or get lower in the front part to reduce your area. Tight-fitting clothing will also reduce CD, and really collectively, these both tight-fitting clothing and aero position also, they influence both parameters, CD and A. So collectively reduce CDA with these bullets. And these are examples. How to reduce drag resistance force while swimming. And now it's important to distinguish between drag resistance force and drag propulsion force. You want to reduce drag resistance force. Again, by density of fluid, not much you can do. You just pick the swim course that you're at, and that is the density. But maybe you're trying to do some type of world record, and you want to pick a body of water that has a low density of fluid. Swimsuit material, wetsuit material, reduced CD, horizontal position in the water, that could reduce both CD and A. So collectively, we would use these second two bullets to influence and reduce CDA during swimming. How to increase drag propulsion force during swimming. So this is what's going to move you forward. Well, this is your hand area. This is your hand pushing against the water. So sometimes in swim workouts, you put a big paddle on your hand. What are you doing by putting that paddle on? You're increasing the frontal area of the hand. You also spend a lot of time in swimming to work on swim technique because you're trying to increase the frontal area of the hand and the forearm during swimming such that the propulsive drag force is greatest. And that allows you to swim as fast as possible. All right, so those are some application. We'll go through some of those details a little bit more for swimming and for cycling and a little bit for running. But you should know the equation 1/2 rho CDA V squared and be very comfortable talking about CDA as a single parameter. Okay, thank you.